Stellar nurseries are vast regions in space where stars are born. These are clouds of gas and dust, known scientifically as molecular clouds or nebulae, which provide the raw material for the formation of stars. The process of star formation is an intricate and fascinating phenomenon that has captivated astronomers and astrophysicists for centuries. By understanding stellar nurseries, we gain insight into the life cycle of stars, the evolution of galaxies, and the intricate processes that govern the universe. Stellar nurseries are typically cold, dense regions composed predominantly of hydrogen molecules, H2, along with traces of helium, carbon monoxide, and other elements. They often appear as dark patches against the backdrop of the Milky Way or other galaxies, obscuring the light of stars behind them. In some cases, they are illuminated by nearby stars, creating bright emission or reflection nebulae. The temperatures within stellar nurseries are remarkably low, often just a few tens of kelvins above absolute zero. This cold environment allows hydrogen atoms to combine into molecular hydrogen, which is essential for star formation. The density of these clouds can vary, but the regions where stars form, called cores, are significantly denser than their surroundings. Molecular clouds can span hundreds of light years and contain masses equivalent to hundreds of thousands of suns. Within these massive structures are smaller regions of higher density, called Bok globules, which are the sites of active star formation. The internal structure of a molecular cloud is complex, with filaments, clumps, and voids formed by turbulence and gravitational interactions.
The birth of stars within stellar nurseries involves several key stages, governed by the interplay of gravity, pressure, and radiation. Star formation begins when a region within a molecular cloud becomes gravitationally unstable. This can occur due to various factors, such as shock waves from supernova explosions, stellar winds, or collisions between molecular clouds that can compress the gas, triggering collapse. Additionally, the cloud loses heat through radiation, reducing thermal pressure and allowing gravity to dominate. As the cloud collapses, it fragments into smaller clumps, each of which can form one or more stars. As a clump contracts, its density and temperature increase, forming a protostar. This early stage of a star's life is characterized by accretion, where gas and dust from the surrounding cloud fall onto the protostar, increasing its mass. The protostar begins to emit infrared radiation due to the heat generated by gravitational contraction. Conservation of angular momentum causes the protostar to spin, and magnetic fields can channel material into accretion disks. When the core of the protostar reaches a critical temperature of about 10 million kelvins, hydrogen nuclei begin to fuse into helium, releasing immense energy. This marks the transition from a protostar to a main sequence star. The leftover material in the accretion disk can coalesce to form planets, asteroids, and comets, giving rise to a planetary system. This process depends on the mass and composition of the protostar and its surrounding disk. Stellar nurseries come in various forms, each with unique characteristics and roles in star formation. Below are some of the most well-known types. Giant molecular clouds are the largest stellar nurseries, spanning tens to hundreds of light years. They are responsible for the formation of massive star clusters and are often located in the spiral arms of galaxies. Examples include the Orion Molecular Cloud Complex, home to the famous Orion Nebula, one of the most studied stellar nurseries, and the Carina Nebula, known for its massive stars and intricate structures. Dark nebulae are dense regions of molecular clouds that block visible light from background stars. These nurseries are difficult to observe directly, but can be studied using infrared and radio wavelengths. Examples include the Horsehead Nebula, a striking silhouette against the bright background of the Orion constellation, and Barnard 68, a small but well-defined dark nebula. Emission nebulae are regions of ionized gas that glow due to the energy provided by nearby young, hot stars. These are often the sites of recent or ongoing star formation. Examples include the Eagle Nebula, famous for the pillars of creation, towering columns of gas and dust, and the Lagoon Nebula, a vibrant region of active star formation. Studying stellar nurseries requires advanced telescopes and instruments capable of detecting various wavelengths of light. Different techniques provide complementary insights into these enigmatic regions. Optical telescopes reveal the illuminated parts of stellar nurseries, such as emission and reflection nebulae. However, much of the detail is obscured by dust. Infrared observations penetrate the dust, allowing astronomers to see the warm interiors of molecular clouds and the protostars within them. Telescopes like the James Webb Space Telescope have revolutionized our understanding of these regions. Radio telescopes detect emissions from molecules like carbon monoxide, tracing the distribution and movement of gas within stellar nurseries. Stellar nurseries play a crucial role in the universe's evolution. Their significance extends across multiple areas. Stellar nurseries are the only known environments where stars are born. By studying them, we can understand the initial conditions and processes that lead to star formation. The rate of star formation in stellar nurseries influences the evolution of galaxies. For example, bursts of star formation can drive changes in a galaxy's structure and dynamics. The stars formed in stellar nurseries enrich the surrounding medium with heavy elements when they die, contributing to the chemical diversity of the universe. Despite significant advancements, studying stellar nurseries presents numerous challenges. Many stellar nurseries are located thousands of light-years away, making them difficult to resolve. The dense dust clouds absorb visible light, requiring observations at other wavelengths. The interplay of gravity, turbulence, magnetic fields, and radiation creates a highly dynamic and chaotic environment. Stellar nurseries are among the most captivating and significant structures in the cosmos. They are the cradles of star formation, shaping the universe's future and enriching it with light and elements. As our observational capabilities continue to improve, these enigmatic regions will undoubtedly yield even more secrets, deepening our understanding of the universe and our place within it.